Hello everybody. Today I'll talk about distributed computing and facts. So a little about me. So I'm Meni Shmueli, I'm the CEO of DataFlint. My background, I've worked a lot with distributed computing. First as a lead data guy, worked with Apache Spark and Druid and Kubernetes and everything data. And after that, did a very big role as a performance researcher in the data space, basically research how big data distributed computing work, to help it be optimized in dozens of enterprise 500, like Fortune 500 companies. That brought me to DataFlint, which we funded with Daniel here to try to make all of this like a product, which today means basically letting AI be able to optimize big data jobs using context from your production. So this is a little about me. And today when I'm talking about data, really like the current state of where the industry is that single instance engines, which are engines like Polars or DataDB or Data Fusion, were written from scratch from Rust or CPP, and can like run on one machine, but run really, really fast. Those guys, like here is a guy who leads. He like lectured our last meetup, Apache Spark meetup in Brussels a week and a half ago, and he talked about, oh, you don't need Spark distributed engine. You can use you can DataDB in, like if you have small data to like doing your data processing. And the idea is that I call it the single instance engine theorem, that like 90% of your use cases are less than 1 terabyte of data, and if so, like one machine with a lot of memory can do all the processing. And then only like the 10% of cases we need a distributed engine like Spark or database with Spark or Fino or Trino and so on and so on. So this is where the industry currently at, like that's the focus. And everybody's happy, right? One small problem, or big one, it's big data. Basically what happens when you have more than 1 terabyte of data, or when you have like run something in Polars and it works amazing when it's like 1 day, incremental, but now you need backfill it 1 year ago. So what will end up, or like what's currently in work is one of two things. So one is, okay, let's take Polars and let's make a simple distributed system on top of it. Let's use SQS as a scheduler, and let's use Lambda as compute, and let's do some custom logic to split the data. So each Lambda will like read and write 100 files. So that's one option. Take a single engine, try to build a distribution engine. Another solution is to take an existing distributed engine, in this case Apache Spark, and use that for the distributed part, but put some kind of single like instance engine that will run like on each machine. Or in this case, it's Data Fusion. So Spark is using for all the planning, and like the actual compute, instead of Spark and JVM, it's running on Data Fusion. Databricks has a very similar offering called Photon, and so on and so on. The thing is, in both of these cases, we still end up doing distributed computing, which is taking a bunch of machines and making them process data together, right? From a large number of files, they process them and output a large number of files. And that's hard, that's interesting, that's fun. And today in this lecture, I'll want to touch on how this is happening, the challenges there, and how you could look deeper into what Spark and other entities does. So let's start simple. We see distributed computing, we say MapReduce. So what is MapReduce, or how we do distributed computing? It is very simple. We have like an input, let's say the entire Wikipedia articles in the world. It's like hundreds of gigabytes of data. You can take like one laptop and load all this data and compute it and do a word cloud, like how many words, like what is the most popular word on Wikipedia, and count the number of words in Wikipedia. How do you do that with MapReduce and big data? So first, you probably have the input in like a lot of small files, like splits, like let's say 100 megabyte files, and you have like hundreds of them, thousands of them. Then you're doing the map part. You take each file, you're doing some kind of compute, let's say taking a sentence or and like breaking down into words, and then you're doing the initial count, partial aggregation. So you're taking each word and you count it on the input script, on the partition. Let's say Hadoop is like one part in the second part and it's also one the third part. Then we need to do a shuffle. Like someone need to take all the instances of the word Hadoop and count it for final result. So we need the machines to talk with themselves, because the shuffle, to bring all the data to one place. In this case, like one machine will have all the data about the Hadoop code and so on. You should do a hash or a range or like some kind of a way to split the data, so one machine will get all the relevant data from one place. So that's the shuffle part. Then we are doing a reduce. We're taking like the results from all the different shuffle reads and writes, and then we sum up the result. Like one machine said it saw it with one, second machine said it saw it 2 times, so the result is 3. And then we got our final output. So that's basically MapReduce. Okay, how to translate to Spark? So part of the challenge we'll talk today, we have like 2 different views. The first view is what we call like the Spark hierarchy, or like the Spark internal hierarchy, which is where we have a task. Task takes like one split and doing the processing. We have like each task running on a core. Each task is running on a partition, like one like large file or one shuffle block. And like above that we have stages. So shuffle like takes the plan, like the processing and split it in stages, because before we find all the instances of Hadoop, we can't move into the reduce, right? So we need to finish all like the word splitting and counting, and only then we can do the final reduce. Then we have jobs, and after that we have applications. So that's one way to look at distributed computing. But there is another way, which is basically the SQL view. So in the end, when you're using today like a distributed engine, we're not doing a mapper, right? We're not running a mapper and a reducer. We just write a SQL, right? A select, from, where, whenever it's like an actual like SQL or it's like a data frame syntax, we're doing something more declarative. And behind the scene, like Spark or other engine, like using an optimizer to make that into the RDD, or like the resilient, like the distributed part. So we said something declarative, right? Like select from, and we got tasks and stages and partitions. And that's like 2 different views to look at big data. So in this part, I'll jump to like Spark UI, which is when one Spark you got the UI. So this is like an example SQL LM, like just with like data from syntax in Python, is reading some data, then doing a group by and a count, which is exactly what we saw with the Wikipedia example. So I prepared here like a small application. So you can see here, like I just run this code. And that's the exact same group by and count. And say open like locally Spark UI. So here. So we have this like lovely UI, and here we have 2 different views. When we run it, this code, we have this query, query 0. We'll find like a lovely UI that shows that whole state, whole gen, columnar to row, hash aggregate, scan before this metrics. It's really hard to understand what's going on. And there is another view, like another like tab with 4 stages. We can go from jobs to stages. It shows us the distribution part, like how many tasks we ran, where they ran, the duration, number of inputs, and so on. So we have like these 2 views in Spark. But here, when you're using the built-in Spark UI, it has all this information. It has like this MapReduce like show, like it's being shown, but it's really hard to read it. So I tried originally to do this presentation using Spark UI. Just found it too difficult. So if we sum up like the Spark UI, if you have the chance to use it, it's not really well. It's really hard to understand the relationship between the different stages. It's required for this to be used, like what is an exchange, what is not partition. It's not actionable, and the real strategy is slightly. I don't know what to do. So 2 years ago, I decided to do something about it. So I started making open source, which is an Apache license project. It's not sending any data, it's like running locally in the same Spark UI. It's a human level. It's one view for both sequence stages. It's showing you the entire MapReduce process much nicer in one place. It's actionable. It's like taking 1 minute to be installed. It's just like it's not even like record any code or config changes. Just like these like 2 like .config, but you can do it like in the infrastructure level as a script. So you just install a standard Spark plugin, and I think the really good thing is that thing. So how it looks, the same processing when we look at DataFlint. So once you install DataFlint, so here I just added like these two lines, like nothing else. If you want the same script in your machine, you'll get the same results. So once you install DataFlint, you have this button, DataFlint, you can press it, and you can get this nice UI that shows you the summary of the job, how much it took, how much input, output, queues, idle calls, how much memory to use, and so on. So you can see the queries that I ran. We'll start with the first one. So here we can see that we read a file from Unpacked, and we read 2,000 files. Actually, it also shows us something actionable, that we are reading a lot of small files, which are 80 kilobytes each. In big data, we usually want very big files, 100 megabytes, because the storage and the compute is really built in the optimized file, which are between 128 megabytes to 1 gigabytes. Then we take this huge file to have hundreds of fields. We only take 2, right? So we only filter the data in here. Then we are doing a count using partition. We are doing the initial count, the partial aggregation. So you can see that the partial aggregation removes 90% of the data from millions to hundreds of thousands. Then we are doing the shuffle read. We are shuffling 4 megabytes of data. Then on the next stage, right, we need to finish that stage. Then on the next stage, we can shuffle read the data. By the way, the number of partitions is 200, if you know that's the default. So that's one of the challenges of Apache Spark. Then the engine tries to optimize the number of partitions, take it into 3, and then it's doing the final counts. And exactly this data in 20% more. So now we can see more clearly what's happening in the distribution level. Cool. So now we can move on to interesting stuff. So one challenge that we just saw is this partial aggregation, right? We don't have to do this. We can just shuffle the entire data, but we are counting before we are shuffling. So this is really good when the cardinality is low. So here we managed to remove 90% of the data before we send it into the network. So when it helps, when again we shuffle less data, and in this case we exactly the data set was 40 megabytes, but we only send the network 4 megabytes because we already make the data smaller before with an aggregation. And that also makes the merge stuff part much smaller because it merges less data, right? It's just need to summarize or reduce already compute results. But we see a lot of cases where this cardinality is actually high. Let's say we are cutting by user ID and most results are 1. Okay, and we find a very small case where it's 2. In this case, we are just counting the data twice. Once when we read the data, once after the shuffle. So that's completely useless. We're doing the entire computation twice. We are adding another column of the number of counts we did, which does not help, and we should move everything into network. So in this case, this optimization is actually bad. And the interesting news is that Spark doesn't ask you, just doing a partial aggregation every time you're running Spark. Okay, so how can you optimize this, or how we can turn it off? So Spark is very, 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 very non-rigid, so we can tell him exactly what we do. So in this case, we can tell him to repartition the data by the columns, and then basically, once you read the data, just take it as is and shuffle it over the network. And after that, we can tell him, okay, then go by and count. So what will happen in this case is that we skip the count with impartition. We just take the data and write the shuffle it, and then we are doing the count with impartition and count in the same stage, in the same place. And then we don't, if we, the aggregation, the partial aggregation didn't remove any data, in this case, we get a major performance loss because we calculate data once and twice. Another interesting solution here that I'll touch in a second is coalescing before the aggregation. So the bigger the partition, if the partial aggregation works, and it reduces the amount of data, then the bigger the partition, the bigger data we run, the better performance, right? If we run 10 megabytes and remove 90% of the data, we will send 1. But if we run 100 megabytes of data, then we have multiplication marks also that end with like 1 or 2 megabytes. So the bigger the data set, the better the aggregation and the compression afterward will be. So Spark decided, because of reasons, that for the 2,000 files to open here 58 partitions. So let me show you that. So because it's seeing I'm reading small files, it's trying to open like one task within multiple small files. So you can see later you can see the number of tasks. It is like 58. So what we can tell the engine is, look, instead of 58 tasks, just open 6, right? And because the partitions are bigger and we can remove more of the data, then in this case, you can see the aggregation, the aggregated rows are like bigger because we managed to remove more of the data because we only have 6 tasks. So there are, like, we find more duplication and we can remove them earlier. So that's actually a very cool technique. And the challenge of the trade-off is how we get partitions that are big enough that the partial aggregation works, but not big enough that they're not fitting into memory, and then we get out of memory and crash, or we started using the disk, which is also not a good idea because Spark is really optimized using memory. So a cool example of that is an article that Gilad from Similar wrote a week and a half ago about a use case that he migrated job from database to EMR, and database in 1 hour, and EMR ran for 3 hours. And couldn't figure out why. So we used a DataFlint, like a Copilot, and it fixed the problem for him. And in this case, the problem was exactly that, was scholastic. So because of his file was really big, on average 750 megabytes, Spark decided, because it's this parameter, max partition bytes, to take for example, 1 gigabyte file and split it into 8 tasks. Each one by default is 128 megabytes. The idea is that Spark doesn't want to create huge partitions that will overwhelm memory. So we try to split into small tasks. The issue is that it really makes the partial aggregation much worse. So that's the reason it became 3 hour job. Once we fix that with this parameter, we say, look, take this huge file and re-aggregate the entire file. Then instead of 6 terabytes to shuffle, we only shuffle 2 terabytes. That fit into memory, and then we didn't split disk, and then this goes on in 20 minutes. So that's like a real-world example when this kind of optimization or this kind of distributed decisions really make a difference. And if you want to check it out, it's under the DataFlint integration. So chapter number 2 I'll touch really briefly because it's famous and very well known, which is a partition skew. What happened when we have, let's say, the conflicting partition, but for some reason we have a huge partition, right, that has lots of data, so it takes 3 hours to process, but we have lots of smaller partitions, it takes seconds. Then very fast the engine finishes the small task and then need to run the bigger tasks. In this case, by the way, DataFlint will make this lovely distribution chart of the histogram where you can see it very visually. So here the challenge is how we take this huge partition and split it into a lot of smaller partitions. So the classical way we can do that is called sorting. It's like taking each partition in another column, right? Just as random sort, then aggregate based on these columns and the sort, and then doing a final aggregation. So basically, this is the purpose here takes this huge partition, split it into smaller ones, but it has a price because the partial aggregation is much worse. Because now for each partition we have in this example, the sort is 10, so 10 different values. So partial aggregation is much worse, and we're running the entire aggregation 3 times. So 2 count within partition and 1 final count, because we need to count with the sort or without the sort. And then we get worse performance. But if we manage to take this 3-hour partition, make it into a few seconds, that's worth it by a lot, right? So let's touch on challenge number 3. In reality, we usually don't do one aggregation; we'll do multiple aggregations. For example, this business query of how many sales items being sold by more than 3 stores or bought by more than 5 customers, right? So how we do that in big data? So the classical answer, if you write a SQL or in syntax, is we are doing two group bys, right? We are aggregating, like we are counting the store count, we are aggregating the custard count, and then we are reading the data and like doing two joins, right? If we use Postgres or any like a classical system, this is what we do. The issue of the challenge of big data, that I'm going to show you how to explain DataFlint. So this is the query. You can see that I move like the node to only IO, so it only shows like the IO nodes. You can see that we read the entire data set 3 times, right? One to do the first group, second to do the second group, second outputs, and times 3 to read the entire data set, join the results, and then use the final aggregation. So if I move again to take advanced one, so you can do, we did exactly the same concept of the aggregation, right? Once for the store, and then we shuffle the data. We did one map reduce and got the results for store count bigger than 3. Then we are doing the same thing, but for customers that are bigger than 5. Then we need to join the results, read data for the third time, and join the result twice, and then get the results. So that's one way to do that in big data. So you can imagine, like, start imagining the trade-offs of the inefficiency. So there is another way to do that is a bit less trivial, but in big data could be very useful. It's using a window function. So in this case, we are taking the same data set. We are adding 2 columns using the window function. One about counting the for each row the number of stores. One to add the customers, number of customers, and then we filter in place the data, and then we count. Okay? So in this case, it will look like a snake instead of like multiple leaves. So if we run that and we look at the results, you can see it looks like a snake. Why? Because we're reading the data once, we are shuffling, and then we are sorting the data by the first column. Then we are running the window function. Then we are shuffling and sorting the data second time, this time for the customer column, we calculate in the window function, and then we are counting. Okay? So that's the 2 ways we can do distributed computing this query. So what's the pros and cons? So the group by, the more traditional way, is we only shuffle portion of the data. We read the data, we just read one column. Then we are doing the partial aggregation. Then we shuffle only the result of the partial aggregation, and then we count. We are doing a classical MapReduce. Okay? We don't need to sort the data, we just need to shuffle it, right? And different aggregation could be parallelized because of how Spark uses stages. Only when we join the data, we need to run the final step. So we are actually calculating both the customer and the store count at the same time. So that would be very useful. What's the problem? We are reading the data n+1 times. Okay, so for example, from a real customer we had 2 weeks ago, they had a job database, and it ran, it did a 12 group function on 300 gigabyte table. So it basically read 3 terabytes of data when the data set was 300 gigabytes. So one solution could be, oh, you can cache the data in memory, but 300 gigabytes is a lot, it's not fitting into memory. So that's one of the terms of big data. The data we are processing is not fitting into memory. So actually, doing group by reducing the data could be useful, but in this case, it made the data bring data 12 times. Also, this aggregation is in parallel. So they basically, in this case, they're reading the data 300 gigabytes at the same time. So reading 12 times 300 gigabytes at the same time, all the memory is being used for that. So that would be very excessive on memory CPU. But the other way to write it is using the window function. We only read the data once. So in this example, we just read 300 gigabytes of data. But this could be also a bit risky, because how a window automation works is sorting the data, and then we're moving using an iterator and doing a count in place. So the data need to be shuffled and then sorted by the team. And we need to do this process n times for the entire data set for each aggregation. So here we are reading the data twice, so we needed to shuffle and sort the data, like 300 gigabytes of data, let's say, 2 or 3 times. Yes. And finally, the compute is not parallel. We are doing one processing place, which is a bad thing because then it will take much longer, but it's a good thing because we are not overwhelming the memory CPU. So that's the kind of trade-offs and decision we really, like DataFlint, try to give AI all the context, just very good to make better decisions. And that's actually, like, for me, really exciting because, again, that's not trivial. Finally, when you're, let's say we have this data set, complex sets, and we want to calculate multiple distinct values at the same time. We want to know the number of unique stores we have, the number of unique promotions, a number of unique items, number of unique customers. So you would think that will be like exactly like the last section. We need to choose between Google or window function. Like, do we read this data set 4 times, or do we shuffle and sort it 4 times? But turns out in distributed computing there is a trick. And the trick is called an expand mode in Spark. So how it works is that we read the data, we read the relevant column, we are doing an expand, which is taking each row and multiply it by 4, like have 4 copies, and add some generated ID that represent each column to each row. Then we are doing like a classical MapReduce, which is like partial aggregation, so we still manage to remove 90% of the data. Then we shuffle the entire column, the number of data set 1 time. Then we are separating the results, or doing a count that removes like all the rest of the data by like each column where we are doing like a condition, like we are counting how many generated ID generated, then we finish the count. So we just shuffle the data 2 times, and we can calculate as many count distincts as we want. Why? Because we made like a row that is like being generated to represent each value. So that's a really cool trick that you can use with count distincts. So why it's cool, we just need to shuffle the data 1 time. We can calculate as many count distincts as we want, and we don't need any sort to do that. Why it's bad? Because the data is being increased by n times, right? So we have the customer that calculates 72 count distincts, and his data became from 1 terabyte to 72 terabytes, which did not fit into Spark. So in this case, it didn't work, and they actually gave a lecture on the Spark meetup about a really cool solution they did about how to count the data using stochastic results. But in most cases, this is super cool and super useful. And also, like, there will be a lower penalty after the initial distinct, because the partial aggregation works a bit worse than reading data every time. So what we learned today? So first, distributed computing is an art form. You can see essentially like, there is no one solution. Like you have trade-off that depends on your data and the distribution of the data and the problems you encounter. And the engineer actually gives you the power. In big data, you need the power to make a decision how to do the distributed computing plan. Second, distributed computing is all about trade-offs. There is no clear solution. You need to weigh the pros and cons and make a decision. And finally, use DataFlint open source is fun. Thank you.
Thanks to Meni. We have time for 2 questions. If you have anything related to the talk. Cool.
It's a very good presentation. One of the things, I haven't worked with Spark for a very long time, but when you do this windowing and you do aggregation, and then finally you go through a couple phases of shuffling, doesn't that take up a little bit of the network? Because the other question I have is, what size cluster are you running with Spark when you run these metrics, if anything? So that's my question.
Okay, so the question was shuffle and cluster size in Spark. So the idea is usually shuffle is the heaviest operation you do in big data, right? Unless you're in 5% of the cases there's something very, very heavy CPU-wise, like a Python UDF function, but a lot of times the most heavy part of distributed computing is the network access. This is why the single instance engine is so damn fast. And so what you do is that usually you optimize for shuffle, but in some cases you want to optimize for CPU and for parallelism. So that depends on the data. That's an outcome, right? So there's no resolution. It depends on use case, and you can use DataFlint open source to look a bit into it. For cluster sizes, so again, DataFlint open source, you have two metrics. That's the memory and CPU utilization, and you want to maximize them. So you want to choose a cluster that will make sure that you use all the memory and not have any cores that are idle and not doing anything. So what exactly is that amount? It depends on the use case. Sometimes it's mean auto-scaling, sometimes it's mean maybe a bit of a scaling is fine, sometimes we want to eliminate spills. It's very dependent on the use case.
Thank you.
And we have another question.
Yeah. Hey, my name is Krishna. I work for Unpacked. Recently, we are working on a Spark project that for live streaming from AMS topic to Kafka topic. So it's a live streaming. So whatever you covered is not there. So we have three options for streaming. We can use microbatch or the old D stream or the experimental continuous. So our requirement is the AMS, they provide the client, and there is a limitation in the client. Once you create the instance of the client, you cannot create like so many times. So we need a long running process running in a execution mode. So if we microbatch, the problem is if you do the microbatch, the problem is like okay, I can partition by force it to go to one executor node. That I can do by topic.
What's the question?
It's long. It's not one.
Sorry, so maybe if it's a long question,
I can take it afterwards,
talk
but
to Meni afterwards because we have two more speakers.
Yeah, but I can answer a bit shortly.
So the question that this talk and usually big data talks about batches, right? We're talking reading inputs, we're doing segregation, writing output. So what happened when we're using streaming, like Spark starter streaming or other solutions that use different streaming? So the short answer that it's exactly the same. In the end, it's taking a lot of data, right? Split it into different machines and then writing to somewhere else. It's just usually what we call is a micro batch. Instead of a batch of a day, we're running a batch of a minute. Okay? So it's the exact same thing, but it's some different trade-off you need to take. For example, Kafka might have 40 partitions, so you can only open 40 tasks. So maybe you want to keep an exact number of tasks and you can only use 40 cores. Maybe you want to read the data and then repartition it, use 100 or 200 cores. So there are dilemmas there. And regarding micro batch versus continuous, so continuous is basically smaller and smaller micro batch, maybe a second, maybe 400 milliseconds. So that's the exact dilemmas that we talk about micro aggregation and doing pre-aggregation the data. The smaller the data, every overhead that you have, planning the state, reading the data, aggregating, and finding duplications become much worse. So usually the advice is what's your SLA? If it's 10 minutes, amazing. If 1 minute, amazing. Try to make the micro batch as big as you can, because that will optimize the performance usually in a distributed computing environment. Awesome.
But if there's more questions, we should chat afterwards.
Yeah.
Thank you, Meni.